Times. Great. Thanks for remembering to do that, Robin. So welcome everybody. I'm Cindy Finelli and I direct our engineering education research program at Michigan. And I wanted to really thank you for joining us for the first EER seminar of the new year. Today's seminar features Danny Caballero, who's from just down the street at Michigan State. And today, Mark Gusdile is going to do the formal introductions, but I wanted to just take a minute first to thank the community on behalf of both Robin Fowler, who's our EER seminar coordinator, and myself for the overwhelming support that we've seen from the community. We've had a record attendance at our EER seminars. We've had more than 200 unique individuals that have been representing over 70 institutions at our first 5 events.
Woohoo!
Last week, both Robin and I were named faculty recipients of the MLK Spirit Award, in part for our efforts to use these seminars to really amplify the work of minoritized scholars and to showcase research about the experiences of Black and other minoritized engineering students. It's really inspirational to work with such committed colleagues who are so supportive. We're looking forward to a terrific session today from Danny. And as I said, Mark Gusdile is going to formally introduce him. So let me hand it off now to Mark. Thanks.
Thanks, Cindy. I signed up when I knew that Danny was going to be visiting here to be his host before I realized it was going to be all online and there's nothing much for me to do other than I get to introduce him. It's pretty amazing that as a PhD student, Danny helped form Georgia Tech's Physics Education Research Group and graduated with the first Physics Education Research PhD from Georgia Tech. And that's where I first met him. I served on his committee. Danny studies the role of interdisciplinary work, computing integrated with physics ed, how it influences other areas back and forth. Really very exciting stuff. We were just chatting beforehand that I got a chance to visit the University of Oslo, where Danny has an adjunct position with a center that studies the role of computation in science and mathematics learning. So Danny is a learning scientist. He's interested in how learning occurs and how we can help it with various computational tools. And by the way, I want to make sure to point out that you should follow his Twitter feed. He's got a great Twitter feed, and I'm really looking forward to his talk. Thanks for coming, Danny.
Thanks, Mark. Thanks, Cindy. Thanks, Robin, for the invitation. I'm going to try to share my screen here and see what we end up with. So here we go. So I appreciate the introduction. I want to do a little bit of background work because I think it's important to sort of share kind of how we get into academia a bit. I think folks often think that faculty come from the same kinds of places and have the same kinds of experiences, and I think that that's not true. So I want to kind of normalize that discussion a bit. So I grew up in South Texas, deep South Texas, in a city called Mission, which is basically right across the border from Mexico, which you probably would never have heard of. But if you've ever had a ruby red grapefruit, they are grown in that area. In fact, I grew up across the street from a grapefruit orchard in a trailer. This is not the trailer that I grew up in, but it's similar to the one I grew up in, living behind my grandparents' house. And so I spent a lot of time running around and, going through the orchard and stealing grapefruit and stuff like that. My parents really didn't plan for any of their kids to go to college. That's not a thing that was true in my family. Not a lot of experience with that. But I was fortunate in that at the time that I graduated from high school, the top 10% of high school graduates were automatically admitted to every public institution that Texas had. So I was admitted to the University of Texas at Austin with really no understanding of what doing college was and what that was like. In fact, I failed my first physics class, and I'm not sure that anyone could have failed it better than I did. I spent a substantial amount of time hanging out in Austin doing things like this instead of going to class. And I just really didn't know what I was meant to be doing. But after taking some time off and sort of reflecting on working 40, 45 hours a week at a copy shop, I realized that I probably should go back to school and And I was able to fall into a group of people that knew how to do college better and helped me learn how to sort of approach my studies and approach college in general. I then graduated from the University of Texas. I actually graduated with honors, but wasn't able to get into any graduate schools initially. And so I applied to be a pyrotechnician at a school in Florida. And if you want to learn how to do pyrotechnics, there's no better place to learn than Central Florida, because they have lots of amusement parks. But kind of right before I started thinking about whether I was going to do that with my life and move to the Orlando area, I went to the local bar across the street from the physics department at the University of Texas and ran into a friend of mine who also had the same situation where he graduated and had done well in physics and hadn't gotten anywhere, but then talked to our academic advisor and found out that Georgia Tech was still taking students. So I went home that evening after far too many adult beverages and applied to Georgia Tech and actually got in somehow to their graduate program. And I started working with my PhD advisor, Mike Schatz, in nonlinear science. So the work I used to do before starting up the group that Mark talked about was a fluid dynamics group. And I don't know that you can see the video here too well, but it's basically a video of a little droplet bouncing on another surface, a liquid surface. That's kind of where I started my work, but then shifted into working in education research, then graduated, as Mark had mentioned, went on and did a postdoc at the University of Colorado, continuing in education research. And now I've been at Michigan State for, I don't know, 8 years or something now. So now in both the physics department and computational mathematics, science, and engineering. So that's sort of the perspective that I have with regard to academia. And I'm going to tell you a little bit about the research that I have done with folks on integrating computation into physics education. And this is not work that I have done alone. Certainly, it's the work of many people. So I want to show you the current list of folks that work in our research group, faculty, postdocs, grad students, undergrads. As the research comes up, there will be names that come up, and I'll sort of point out the contributions of different folks along the way in terms of this work. So, and I should also say, feel free to like ask questions. I'll try to keep track of things, and maybe, I don't know, Cindy or Mark maybe can jump in if something comes up.
Yep, we'll be here watching.
Thank you. So my department's a big physics department, just like the one at the University of Michigan. We have two central goals. One is conducting original research, and as you all know, we have the National Superconducting Cyclotron Laboratory, now the facility for rare isotope beams, where we study some of the underlying physics associated with nuclear processes. And a lot of work is devoted to that. The other principle, or the other goal that we have, is educating the next generation of students. Those could be students who are going to become scientists, engineers, teachers, and even folks that are not going into STEM. The pictures on the right here are pictures of my colleague Vashti Sautel's Introductory Physics for Life Science class, where students are building models and experiments to investigate the properties of physical systems. The way that I think about my work is an interconnection between the two goals that we have for our department, in that I do research that can support education, and historically that work has been in physics, and so I sort of situate myself in physics education research, which is, I think, got a lot of similarities to engineering education research, in that we study student learning and engagement. We do pedagogical and curricular impact studies. We look at how students are recruited into and retained in the major. We investigate issues of diversity and inclusivity in physics environments and in physics programs. We look at how faculty engage in their practice, how they make decisions. We study departmental culture and climate. And we look at national landscapes that surround physics and physics education. So effectively, if there's an intersection here between physics and education, there are often people who are studying it. And we draw on the three areas of research, both our theory, experiment, and applied work, where we're building theory, working on understanding how experiments can be conducted to look at different outcomes, or applying our work to specific environments and spaces. I consider myself to be a more of an applied researcher than theory or experimental. Just if you're really interested in learning about physics education, there's actually a book on the entire history of the field and sort of where it's going, that was commissioned by the National Research Council. And now you'll see how quickly I put together these slides. So this is the field of physics education research as it exists, and part of this talk was given at Cornell at some point, obviously. But there are places all over the United States that do physics education research. There's a lot of big questions in PER that we investigate. There's sort of these principal directions that may be a little bit different from engineering education, because we're often a service department who is facilitating the education of folks that are not in our major. We teach a lot more students than we have in our major. So one of the things that we've focused on historically is looking at issues of peer collaboration and evidence-based techniques, particularly at the introductory level, and specifically for students who are going to become engineers, and also students who are going to become life science or bioscience folks. One of the things that's interesting about our major is that the participation in physics hasn't really kept pace with the rest of STEM. When you look at the numbers of students that are participating in physics as a major or graduating with physics degrees, it's been relatively flat for the last 30 or 40 years compared to the rest of STEM. And that's actually broken out by different majors. It can't be really attributed to the growth of, say, computer science or something like that. The other thing is that as in engineering, women and students of color are significantly underrepresented in physics. What you see is that about 20% of the students who are earning physics degrees are women. About 20% of the students who are earning graduate degrees in physics are women. And yet the participation in high school classrooms in physics is around 50% women and 50% men. Students of color, on the other hand, you start to be able to count individual people. The year that I graduated with my PhD in physics, there were around 6,500 folks that earned PhDs in physics in the United States, and there were 11 of us that were Hispanic. Physics is changing. There's a lot of new tools and new techniques that are being used. We're borrowing techniques from data science to do research. There's a lot more automation, and there's just a lot more use of this tool. There's a lot more use of the computer in everyday physics practice. And so the kind of work that I'm interested in is trying to understand how we can incorporate it in ways to help students engage in physics practice that is representative or more representative of what we actually do. So I have some high-level examples of this, which are a little bit dated, but I think they're some of the highest level ones that we have. Here's a picture from the conference room at CERN, the day that the Higgs boson was discovered, and people are super excited, and they're super excited because of this figure here, which is showing the detection of that Higgs boson right there, that little bump. And that little bump is the result of an analysis of something like, I think, 1 million DVDs worth of data. The LHC generates data so quickly that it actually can't be written to disk. It has to be evaluated and discarded quickly because there's just a tremendous amount of it. And the amount of computational work that's necessary to sort of get these points and these error bounds is just incredible. Not to say that the experimental side isn't incredible, but it's just immense what we're doing. This one, also a little dated, but is a description of the, I'm sorry, a New York Times article that describes the observation of two black holes colliding and merging. This is actually from the second one. And since then, we've seen a lot of other kinds of cool astronomical objects that have collided. But the data that was collected around this is here. These are from the detectors in Hanford and Livingston. And here's this black hole merger ring down that was observed. And what's really incredible about this is not just the experimental work that was done to build these detectors, but the analysis that's done. If you look at the scale here, you're talking about a strain that is on the order of 10 to the minus 21. And my understanding is that's basically detecting a signal that's the width of your thumb compared to a length scale that is, you know, the distance between us and the next closest galaxy, right? So the level of sophistication in these analyses to unpack this is just incredible. So computation is really how modern science is done. I mean, this analogy of a three-legged stool that sort of have these three things that support our work is I think apt for what we're trying to understand here. But we can ask a question about like what's changed in physics education over some, let's say long period of time, right? So in the 1860s, we had a lot of folks that were investigating electromagnetic phenomena. We had the development of Maxwell's theory of electromagnetism. And this is a beautiful theory. It's very complete and it's classical, and yet it sort of describes some really interesting things that we didn't quite understand at the time, like the speed of light being constant, for example. But if you look at a textbook at that time, this is what you see is the Atwood's machine, which you might be familiar with. And I'm sorry for triggering anybody who's had to study this thing. The idea is that you have these two masses, one on either side of a pulley, and the objective is to sort of predict the motion, right? And that seems like a thing that would be, fairly reasonable for people to be doing in the 1860s, right? Engineers were lifting heavy things to sort of build buildings and so forth. So maybe that's important. We go forward a little bit, maybe about 40 years or so, and we have the development of the special theory of relativity in the early 20th century. We have the observation of and the prediction of the photoelectric effect, which starts to help us understand quantum mechanics. And we look at a textbook at the time and we see the Atwood's machine again, this time in incredible detail. This is from a German military manual, and it has a substantial amount of shading and perspective. It's quite beautiful, actually, when you look at it. All right, but let's go a little farther forward, another 40 years or so. We have the development of radar, the development of the laser, right? We're starting to see the beginnings of solid state physics. And we look at an introductory physics textbook and we see the Atwood's machine again. And now it has some numbers so we can actually do some calculations, I suppose. Notice that they're in pounds, not in kilograms. That's interesting. In the 70s and 80s, right, so you have the sort of development of nuclear power. You start to see the personal computer come into play, and that personal computer can be used to draw the Atwood's machine that appears in the introductory physics textbook, now in grayscale and clearly drawn by computer. This is when I was in college. This is a map of the internet at some time with interconnections between different computers and so forth. And we have these devices in our pockets now. This is an old one, but that have access to this information that can do sophisticated calculations. And so now we can make the Atwood's machine be in color because we don't have to print it anymore. We can just show it on the screen, right? So the point being is that we haven't really done a lot with introductory physics, but I would argue that a physics education requires us to have a computational education. And there's a number of reasons for that. So here's a photograph of a formula sheet from a quantum mechanics class. And that's actually what I'm teaching right now. But what you can see here is that the student has written up all of the formula that are relevant for this particular quantum class. It's also partitioned off in blue pen to indicate, what equations go with what other equations, right? And really, this is a challenge because this is what our students often see our introductory and advanced physics courses to be, is this collection of equations that are meant to be activated at specific times, right? And they kind of go together, and that's what we do, right? That's how we construct environments for them to make use of these ideas. And what's not apparent is the underlying models and the underlying physicality that goes into these descriptions and understanding how those relate to each other. In addition, right, computation affords us visualization. It allows us to make conceptual sense of situations. So here's a particle in a box and a particle in a harmonic oscillator, and what you can see is the time evolution of the probability distribution of the particle, and start to make some sense of what happens to the particle, where we might expect to see it and why. In addition, there's this generalizability to computation that it affords, right? No longer are we limited to studying specific kinds of problems. We can really study classes of problems and use the same tools to investigate them. So, for example, this differential equation may describe the buckling of a beam. It may describe the potential between two plates. It may describe a potential well. It could describe a model for diffusion. And really all that matters is the differences in our choices of A and B and our interpretation of what U is in this case. And the tools that we use to solve these problems are all roughly the same. So in physics, we've done a lot of studies, I'm sure engineering has done them as well, where we try to understand where our physics grads go. So in, almost 5 or 6 years ago now, there was a study done of bachelor students, and we found that about 55%, 54% of them go into graduate school after their bachelor's degree. Most of this is in physics and astrophysics, engineering, computer science, and so forth, mostly in STEM, right? But there is about 46% of our students that go directly into the workforce. It's interesting when you look at this at different institutions, because the fractions are very different if you're looking at, say, Yale or Harvard or the University of Michigan, and comparing that to, say, MSU, where more like 70% of our students go into the workforce and maybe only 30% go into graduate school. So we're maybe a little bit more interested in workforce development. If we look at the students who actually go into the workforce, we find that the vast majority of them are going into STEM careers, and those careers involve them doing programming, data analysis, modeling, and so forth. So it's a very large fraction of students that would benefit from learning about how to do computation in physics, to be able to not only apply that to physics itself, but also to other spaces. So the thing that really drives the work that I do in this area is, like, how do we actually integrate computation into these physics courses? How do we go about doing that? And so I'll start with a conversation that is a paraphrased discussion at a large Midwestern university. And so Professor 1 says, I want the students to use computers to solve interesting problems. Professor 2 says, then have them code. Professor 1 says, this isn't a CS class. And Professor 2 says, well, then don't have them code. And Professor 1 then says, well, then I can't have them do the interesting problems, right? This is a common conversation that I've had with faculty at a variety of institutions, including a particular large Midwestern one. But the answer is really that it's quite complicated to do this work. And I think the reason that it's complicated is because there's a lot of layers to doing it. And so I take a framing on this of sort of different contexts in which we would try to make these changes and understand what happens. So we work at a college or a university, and within that college or university, I work within a physics department, and that has a certain relationship with that college. It has certain resourcing. It has certain expectations on it. Within my department, we offer certain kinds of courses that have certain populations that take them. They have certain prerequisites or co-requisites. They have a certain pacing or expectation to complete certain kinds of things. Within that course, we have a class meeting, which may have a specific structure to the classroom. It may have a certain number of students that have to take it. It may be resourced in a particular kind of way. There may be expectations from the faculty member or the instructors or the students for that class meeting to run in a certain kind of way. Within that class meeting, we may have activities that we do that are, again, sort of dictated by the way that the meeting occurs, what's expected of it, what the students are ready for. And within a given activity, you may have a specific task that you want students to engage in. And that might depend on where you are in the semester, or what the students have had prior to that, or what you expect them to be able to do afterwards, right? And all of these frames of context help us understand how complicated this problem is, because all of these layers talk to each other and they all interact with each other. And so the kind of research that we have to do when we're making these large changes is to understand not only the individual context, but how they relate to each other. And so this framing is the way that I think about the different kinds of work that I do. And so what I'm going to tell you now is some stories, some research stories at these different levels, these different frames. Let's start with just who teaches computation in physics. So this is kind of a large question at the sort of highest level. And this is some work that I did with some folks at Yale and the American Association of Physics Teachers and the American Institute of Physics, where we developed a national survey that was distributed to physics departments across the country to understand how folks are teaching computational physics at the moment. And the way that that worked is we worked with AIP to build the survey. We sampled departments across the country. To give you context, there's about 760 or so degree granting departments in the United States in physics. There's another 1,200 or so two-year colleges that teach physics. So our sample is maybe around a fifth or a sixth of departments around the United States. Then what we did was, through that sampling process, we actually just emailed every single faculty member in the department to get them to respond to the survey. So we ended up with more faculty responding to the survey than departments, because we wanted to sort of see what was going on there. Now, AIP, as you might expect, is a institution that knows how to do surveying, and they really pushed us to define computation for the survey, because there's a lot of different ways that we could talk about it. And so we came up with a preamble that preceded the survey to sort of explain to everybody what the different ways we might discuss computation in the survey. So simulations or algorithms where students work with them, giving students pieces of code, advising students on undergraduate research projects, etc. So I'll just give you some quick results from the survey. What we found was that more than 50% of departments have a majority of their faculty teaching computation, as defined, as we said. We think that number is quite high because we think both our definition is quite inclusive, and also that the people who tend to respond to the survey are people who probably are interested in using computation in their courses. I'll tell you a little bit more about that in a sec. But when we break it down and look at the specific courses, departments seem to suggest that that they're teaching computation in equal measure in introductory physics and advanced physics courses at a rate of about 25%. When we ask them what kinds of things they use to teach computation or have students do computation, what we find is that a lot of faculty deliver computation via homework and projects, which makes a lot of sense. It's, students can sort of use those, can do those things outside of the classroom, but fewer of them have developed interactive activities for students or have things that they would refer to as assessments of student learning, in the sort of traditional, more high stakes sense for computation. And so some of the takeaways from this very sort of short introduction to what we're doing is that a majority of faculty that we surveyed report having experience teaching undergraduate students computation. We think that that number is high for a couple of reasons, and I'll show you some analysis we did to sort of show that that was the case. But we think that computational instruction is more prevalent than it was in the past. As I said, the number is close to 25% in courses. A survey that was done over 10 years ago, similarly done, showed that that number was more like 10%. So even though we have a high number, there seems to be some growth over the last decade. One of the things that's interesting is we're lacking formal computational physics programs. Only 7% of the programs that we surveyed actually have a degree program where computational physics can be a specialization. And this work indicated to us that there's a need for us to explore interactive methods and assessment techniques for computation, which I'll come back to near the end. But we were super interested in who these people are that teach computation. So my student, Nick Young, along with Grant Allen, who was an undergraduate student, my student, John Aiken, and my postdoc at the time, Rachel Henderson, we did an analysis of this survey using a technique called random forests, which allows us to predict whether somebody is teaching computation or not, or reporting that they teach it or not. based on a survey that has a wide variety of scales. So, the kinds of questions that we were asking folks might be on a Likert scale, where they're being asked like, computational physics is hard to teach. My department rewards me for teaching it. There's no institutional support. My department considers computational instruction when hiring new faculty, et cetera. But we also had demographic information, school information of those folks. And so what I'm going to show you here, I don't want you to pay too close attention to, we'll zoom in on it in a minute, but these are the importance factors. You can think of these you can think of them like an odds ratio. They're really not, they don't have the same interpretation, but larger means that it's a better predictor for the model than smaller. And so by doing some iterative work on this, Nick was able to show that there's 5 key questions that really were predictive of whether students were, or whether faculty were reporting that they had experience teaching computation or not. And that was whether they used it in research with their students, whether they reported not personally using it, whether they believed it allowed them to bring in new physics, whether they felt that it allowed them to bring in new problems, and actually the highest degree that the institution offered. If they offered a bachelor's degree or above in physics, they were more likely. So Nick looked at these in detail to sort of show with a bit of a gut check that, yes, indeed, people who use computation to provide research experiences report teaching students to use computation. When they think that it brings in new physics, they tend to report that they teach computation, et cetera. What was interesting were things that were like the undergraduate program in my department values instructing physics majors. This was actually not a factor. And it turns out that all of the institutional and departmental factors didn't actually predict whether folks were teaching computation or not in their program. So this tells us that of the folks that we surveyed, those that responded tended to not be motivated necessarily by the department or the college and the sort of support structures or the values that they may have around this, that they're potentially treating it as an individual choice. They use it in research, they believe it brings in new physics and new problems, and they teach it at institutions that offer a bachelor's degree or higher. So these folks tend to treat it as an individual choice. For a moment, I want to just stop for a second and actually say something a little bit about this issue with which bachelor's degree institutions. Two-year colleges are really, really important to the educational system, particularly for MSU. We have a lot of students who transfer from two-year colleges into our STEM programs. And if folks in two-year colleges are not reporting teaching computation to students, then they seem to be like a really important population to talk to about how that could work for them. In particular, because of supporting those students into the major, but also because the diversity of students who attend two-year colleges and then go on to four-year colleges is significantly higher than those who go straight into four-year colleges. So if we're looking at issues of diversity, equity, and inclusion with regard to STEM majors, we should be looking at two-year colleges as just an aside. This leads to a lot of open questions, right? How do we support a broader cross-section of faculty to integrate computation? What can departments actually do to support moves to integrate it? If these levers don't seem to be useful for the folks that we're seeing right now, are there levers that are useful for other folks? And how do we help faculty design courses, curricula, pedagogy, et cetera, to teach this effectively? I'm a part of a larger group called the Partnership for the Integration of Computation in Undergraduate Physics, which is a mouthful, but the acronym is PICkup. And PICkup is working to support faculty in physics and astronomy to teach computation in their courses. This is pre-COVID, when we could actually have in-person workshops. And we had about 65 faculty from across the country come for a week long to hang out with us in River Falls, Wisconsin, and learn how to integrate computation into their courses. We've run this workshop for 4 years. We did not run it this year, obviously. But we are looking to continue to run this in perpetuity because there is just a demand. It's grown from 19 people attending to having to turn folks away because the room is too small. The workshop participants come from all over the country. And they engage in a variety of class planning activities, backwards design, et cetera, assessment development. In particular, we try to engage them with these so-called exercise sets where we have these longer designed activities with learning objectives and class notes and so forth. This is developed by a colleague of mine, Ernie Berenger, who's at Eastern Michigan. This is for a classical mechanics course looking at a 3-bar pendulum and sort of how you model it and what kinds of physics you can understand from that. This is an old plot, but it shows the growth of the group over time. We're well over 1,000 verified educators now. Our Slack membership is around 500 or so folks. Active participants probably closer to 100 or so. So there's a pretty active community. Again, from all over the country and in fact all over the world. One of the things that I love about working with Pickup is that I get to talk to like regular research and teaching faculty who don't necessarily have an educational research bent. And so they give me lots of really interesting questions that lead to research studies that we might investigate, right? Things that are really impactful for them. Like, you know, how do you do this across your department? What might you have to give up if you're going to integrate computation? How do you know your students are learning? What's the best format, et cetera, et cetera, et cetera. So a lot of these things have actually driven much of the research that we've done over the years, is just listening to people and saying, let's see if we can figure that out and try to understand it. So narrowing it in scope, I want to talk a little bit about how you might integrate computation across your department. Now, I know this is not a departmental colloquium, but it's something that I think is interesting for programs to think about, is how you do this across larger systems. And so I'll start with a little bit of a disclaimer. Your mileage might vary significantly when thinking about how to do this. So there are some substantial challenges for an R1 school. Resourcing is one of the largest ones. We are a service department and our service courses make money. If we can put 300 students in a classroom and have one instructor in front of them, we are making a substantial amount of money for the department and for the university. So our courses are taught at scale. And so anything that we change needs to scale. We teach about 1,000 students per introductory course. We teach about 100 students per advanced course. And anything that we decide that we're going to implement has to fit that model. The research and demands and expectations on R1 faculty are pretty high. So the investment from different folks varies quite widely. And we do a lot of our instruction with graduate students and undergraduate learning assistants. So there's a lot of professional development that's necessary for folks who haven't been in the classroom before, or folks who may be teaching their peers. At MSU, we have a large, diverse faculty. So again, the interest varies quite widely, but big changes in our department mean big discussion. We have about 65 faculty from a wide variety of disciplines. So having a discussion about when we're going to make changes is quite a long process. But our department had a lot of positive pressures. We had a supportive administration. Our dean is a computational physicist. Our chair is an astronomer who does sort of data science focused astronomy. Our undergraduate chair is supportive of making changes to the undergraduate program. These demands and expectations actually can be a positive because people can be awarded grants for educational transformation, which includes my colleagues in, say, biophysics who've been applying for grants. We have a physics education research group, and so us getting grants and executing this research is important for us. Our large diverse faculty has a lot of progressive junior and mid-career folks that understand that physics majors do not go on to be physicists like them and want to build a program that represents that. And we've done a lot more hiring in computational physics because it's the direction that our department is going. And we've had some state level investment. We have a new STEM building that's in the process of being finished that we hope to be able to teach in the fall of 21 as long as things go well. But it will be done in fall of 21 regardless. So just to give you a timeline, this is our typical course progression. Students take introductory mechanics, E&M. They take a course called CMSC 201, which I'll tell you a little bit about. Modern physics, class mech, et cetera, for the advanced courses. What you're going to see here are yellow indicators which tell you that the course is using a computational environment for plotting or something like that. Light green is some sections are teaching computation to students and having them actually do it. So think about giving students code and working with it or having them write it from scratch. Dark green is that there's actually instruction and computation across all sections. And black means that the course actually isn't offered. So we have some courses that we only offer once a year. So in the fall of 13, at the beginning of time, none of our courses were teaching computation. That's when I started at MSU. And then we got some funding to develop an introductory mechanics course with computation. And so for the next couple of years, we worked on some sections of that course, teaching it with computation. And we started to see some of our colleagues pick up these ideas and say, hey, that sounds pretty cool. You can do that with intro students. Let me try to do some things in some of these other courses. In 2016, our chair formed a committee and said, you need to investigate integrating computation across our program. We got to see how that's going to work, and we want to try to do it. And the Department of Computational Math, Science, and Engineering started. In addition, we got more funding for the development of an intro E&M course. And so in the next year, some of our students started taking this 201 course. We hadn't yet required it for them, but you could start to see that we started to implement computation in some of the advanced courses, and particularly E&M 1 and 2. Those were where the pilots started for the departmental committee. The following year, we had a unanimous vote that we should try to integrate computation into our courses within 5 years, and that we were going to require our students to take CMSE 201, this Introduction to Computer Modeling and Data Science. And so now you see, at least up to 2019, that the experience is such that students will have a lot of computational experience through the major. So you start to see modern physics, classical mechanics, E&M 1 and 2, StatMech, and the PER faculty that were involved are the ones with the stars there. So you can see even non-PER faculty are starting to teach these integrated courses. And I haven't actually built this up going further, but actually Quantum 2, the course I'm teaching now is another pilot, has computation in it as well. And the idea is that in the fall of 21, we would try to be at the point of having a fully integrated curriculum with all of our intro courses having computation, including the one for physics for life sciences, which has been a big change over the last several years. So let me just tell you briefly about this Introduction to Computational Modeling 201 course. This is a course that's taught not in computer science, but in our computational mathematics, science, and engineering department. It's taken by STEM majors. It has a Calc 1 prerequisite, that's it. So they just have to have differential calculus. And it's required for physics and astro majors. It's taught to about 50 to 70 students per section. They used to sit together, now they sit on Zoom. I taught the follow-on to this course last semester, and it's taught in a flipped model where there's some pre-class assignments, and then they do some small programming assignments outside of class. If you're interested, I can send you the paper that details the course. This is what it looked like when it was taught in person. This is what we hope it'll look like in the fall of 21. You can see students sitting around a table here. All of them have computers. They can talk through their analysis that they're doing in the classroom. My colleague Mike Murillo is looking over a student. In fact, the table in the back is all physics majors, including 2 graduate students that we currently have. The kind of activity they may do in class would be, say, modeling like a bungee jump, right? So students work through this code together in Python. They start with modeling a skydiver falling without air resistance, and then they build up an air resistance model, opening a parachute and a bungee jumper and so forth. And it's now required for our students before they take class mech, so we can build on that understanding using Jupyter and Python to bring in new modules, tools, libraries, and so forth for our advanced courses. So this is just kind of how we've started to do it. There's a lot of different models that can be done. One of the things that's still outstanding for us and for others is what students have learned after they've been instructed in computation. We've been designing a lot of environments, but we haven't really unpacked their understanding. And I'll apologize to Mark because these slides have not changed in 10 years. We often in our introductory courses teach students to use minimally working programs where they're given a piece of code and they have to fill in the bits that are missing based on a situation. So this is Python code that models the motion of a satellite around the Earth. And what students will have to fill in are the objects that are created, the parameters and the initial conditions, and the calculation loop and other sort of visualizations, which are in purple. So when I was at Georgia Tech, we did this study where we taught students how to engage in this kind of minimally working program approach, and then we investigated whether they could do this by themselves in sort of a proctored environment. And so what we did was we gave them a new model that they hadn't seen before. They had to alter or add all of the red bits and then turn in their code, and their code was checked against the results that they should have. And we found that over 3 semesters that roughly about 60% of students were able to model things correctly, and maybe 40% or so had 1 or more errors. What was interesting to us were the students that didn't have correct code. So my advisor and I went through and we looked at all these pieces of code and we scored them on a rubric looking for different kinds of things that they did. Turns out that there were like 128 different ways that students could go wrong. So we used a clustering technique to understand the relationships here and potentially group things. And what we found, and I think actually Mark pressed me on in my dissertation, as I remember, was this claim that the dominant errors that we saw students make were not syntactic. We found about 80% of students appearing in just 5 clusters where they made a sign error. In the force calculation, they ran their code correctly, but it had an error in the initial conditions, had a typo. They treated their net force as a scalar. They treated the separation vector and raised it to a power, which is a mathematical no-no. They calculated the force outside the loop, basically treating it like a constant force, etc. And I think at the time, Mark asked me the question about how do you know that? And then the answer that I bumbled through was enough to grant me a PhD. But I think over the years, I've become a little bit more thoughtful about this and actually realized, like, I don't know that we can actually separate these two things, because over time, I've come to understand the relationship here between these different knowledges and practices, where the overlap here is that we're bringing in physics, mathematics, and computation into the same space and asking students to contextualize that to do computational modeling in physics. And how that knowledge gets activated and used and how those practices get engaged in depends significantly on the history of students' experience in these different environments, and also their, epistemological stance around what they're supposed to be doing at that time. So this led me to a lot more open questions than I think I appreciated at the time, right? How do students even go about constructing these programs? What knowledge and ideas do they leverage when they engage in this stuff? What are the patterns of participation that we see? And what forms of instruction support different kinds of outcomes? These are all super important questions if we're going to start trying to decide that we want certain kinds of outcomes or certain kinds of patterns of participation in our courses. So I'll end with one such study, which looks at how we teach computation in our introductory physics courses at MSU, and a study of undergraduate learning assistants. So right now what we do is we have students engaged in a problem-based learning course. It's not problem-based in the same way that you call it in engineering, but it's a little more limited in scope, in the sense that students engage for an entire day on one large problem. So here are 2 days worth of activities. The first day is students have to engage in a calculation to determine how to put an object into geosynchronous orbit, and then they have to model it on the second day. And the way that we go about doing that is we have students working in small groups, about groups of 4, and we have a lot of learning assistants that are teaching these courses with us. The thing that we were very interested in was, what is the relationship between the way that different learning assistants teach computation in these environments? The picture here is actually of a student of ours, Katie, who taught introductory physics for 7 semesters, which, if I understand correctly, is like 4 semesters more of teaching experience in physics than first-year physics teachers have when they go into the classroom. Katie was a highly qualified physics teacher. She went off to be a law enforcement officer in Dallas, but we couldn't convince her to stay in physics. So one of the things that we were interested in, this was work that was done by my graduate student, Alana Pollack, was how do learning assistants approach this teaching? So I won't bore you with the details. It was a phenomenographic study where she interviewed something like 15 or 20 learning assistants, and she developed some themes that describe the ways in which learning assistants approach their instruction. One of the themes was about the utility of computation. This was the LA's perceptions of usefulness of computation, either inside or outside the classroom. The second theme was what the outcome the LA wants from their students. That is, what do they want their students to take away from computational problems? The third was a characteristic that the LA tried to moderate, like what are they paying attention to when they're working with their group to try to influence in the instruction? And the last was the strategy that they employ in teaching computation. So the way Alana that constructed this was by looking at the different themes and the variations that she saw. So as an example, let me tell you about teaching strategy, right? So the theme is the different ways that an LA may teach in the environment. So they may focus on helping students navigate programming errors. They may leverage the affordance of computational problems to show them that they can use it in different spaces. They may encourage their students to reflect on the coding that they've done and how it relates to the physics, or they may leverage collaboration rather than doing the instruction themselves. They may push the classmates to sort of interact with each other. What this results in is a category of description. So by linking together each of these themes, we get a category here. So for example, if a LA thinks that programming is an important skill, that's its utility, then they may focus on teaching programming skills. And so they may try to get students to work at a specific pace so that they can have more experience with those programming skills. And thus the strategy may be to help students navigate those programming errors so they get more experience writing programs. So just quick examples of that. Here's a quote from Kendra, who was categorized as focusing on navigating programming errors. So she says, most of the time I just teach them how to do it. She's talking about how to deal with errors, because it's usually when they're just like edited like one line of code, and then it's like, oh, we have a tabbing error, and I'll just be like, here's how you solve that, highlight it, and then do the thing, and then yay, it's good. And they'll be like, okay, cool, now I know how to do that in the future. We can contrast that with Molly, who leverages collaboration. So in her quote, she says, I might say something like, ask a group what they're doing. And if someone responds and it looks like the other two aren't paying any attention, I might ask, oh, are you guys good with that? Or like, are you guys on the same page? Or do these guys understand that? Or something to get that sort of conversation going, right? So in the work that Alana did, what she was able to describe was different categories that our LAs might be using in the classroom, whether they're sort of focused on narrow programming aspects, learning conceptual physics through computation, learning how to use computation as a tool for doing physics, or shifting students' perceptions of what it means to learn physics. And she argued that her outcome space was hierarchical in the following way, that this builds up sort of increasing levels of sophistication with using computation in our classes, and that what we might really want to try to do is try to understand these top two levels and how we may support our instructors engaging with those top two levels if those are the things that we really want to see as outcomes in our introductory physics classrooms. So this leaves us with a number of open questions yet. How do different instructional approaches by LAs lead to these different outcomes for students? We actually haven't connected this to students. How do these approaches by LAs change over time? This was taken at a particular snapshot with different LAs at different levels of experience, but do these things shift over time? Are they contextual in some way? How do we support the instructional approaches that lead to the learning we actually want to see, right? If we care about those top two approaches and outcomes, then how do we actually build professional development to do that? And really what's interesting to us also is how does this apply to faculty and graduate students who may have more experience with computation than undergraduate learning assistants? Are there different categories? Are there different nuances here? So I'll end with a long list of additional research that we are engaged in. I didn't talk at all about the high school work that we're doing. I didn't talk about some of the clinical studies we're doing. And I didn't really talk about all the design work that we're doing either, but there's a lot of different things that are going on in the lab around computation with a lot of different folks that are participating in it. But the punchline is really that the work that we do in education research and physics can help support the integration of numerical computation. And that's if we do research with students on activities, pedagogy, and curriculum, with faculty, and with departments in larger systems. We need to understand all of these different relationships. So I'll go back to the slide that I started with, which is, this is the way that I sort of think about my work, is research that supports education. And that's impossible without embedding that in a community of support. And so I want to show you the people who are really important to me, the group that I work with. I get to hang out with these folks every day, and you know, having not seen them for a year has been really hard. I miss them a lot. So thanks a bunch.
Thanks, Danny. That was amazing. Clap, clap, clap. Let's see. So you can put questions in the chat. And oh, I see there's a Q&A thing that I haven't even been looking at. Okay. Corey asks, could you share thoughts on ideal language to teach computation with? Is there work on this?
That's a good question. I think that there's a lot of conversation, in particular in computer science, and Mark, you know this well, right, is about different languages and approaches to teaching computational ideas and practices, right? And there's a lot of attention that's paid to the different structures of those languages and the ways in which the ways in which people understand them and what they actually learn from them. And that is not a conversation that we have in physics. And the reason for that, I think, is because we are often focused on training people, right, or teaching people to become professionals in the discipline. And so what we do is we borrow from the professional languages and approaches and sort of fit into that. So the reason that we use Python, first off, because it's free. Second, it has a lot of libraries that we use in physics, and it's really easy for us to plug it into different spaces. I've worked in places where we've used MATLAB. I've worked in places where we use Mathematica because that's what people are comfortable with. I think there's a lot to be said about like how students understand that dynamic of what the language is doing and what it's like, how it relates to their understanding of how the computation leads them to do science. But we don't necessarily focus on it because it's mostly about getting you to do the science we want you to do with the tools that we often use.
Cool. Corey's next question, and I'll get to Robin's after this. Is there some argument that those basic intro to physics problems, the pulley thing, are the idea of the physics, whatever that may be?
That's a great question, Corey. I don't know, honestly. Like we don't teach the pulley in any of our changed introductory physics courses anymore. I have definitely heard people say that there are these sort of canonical introductory physics contexts that teach you about specific kinds of physics, like accelerated systems or conservation of energy or what have you. I just think there's so many contexts in which you can learn those concepts that I don't know that that's necessarily the best one. I don't know. I think we do it because we've always done it. Like at some point in the 1960s, introductory physics was fixed when whoever it was, Resnick or whatever, brought calculus into physics, and everybody has been making a derivative textbook from there.
I think that part of what Corey's asking, and I'm going to put words, and she can tell me if I get it wrong. In computer science, the most popular textbook now is How to Think Like a Computer Scientist. This notion that there is a way to think, that there's an engineering mindset, that there's a physics mindset, there's a computer mindset, and part of computer science, part of what you're trying to convey is this approach or mindset. Do you see that as being part of what they're trying to do in intro physics?
That's a great question. So thanks for the articulation, Mark, because I think the physics mindset is not something I thought about, because I think it's a difference between engineering and maybe physics. We think of it a little bit more like what are the disciplinary practices that we want students to engage in. So you could think of that as mindset, or you could think of that as like the culture of doing physics, and how does that translate over to the classroom. So one of the things that maybe speaks to what Corey's asking is like, we all say we do modeling, like we all model physical systems, but is modeling a physical system solving the Atwood's machine problem? I would argue probably not, because it's a highly constructed example that has a very particular solution, right? Whereas taking a real world situation and boiling it down to an Atwood's machine, right? That's building a model, that's making assumptions, that's constructing a mathematical model that happens to be the Atwood's machine. So I think physics is moving more towards that approach of like, how do we take those disciplinary practices that we engage in to understand the world and actually build curriculum and pedagogy around that, as opposed to specific types of problems.
Robin's question, and did you want me to read it, Robin, or do you want to just shout it out?
Okay, so basically I wondered whether it sounded like the interpretation is that the learning assistant strategies are based on their perception of the utility of computation as opposed to affected by their perceptions of the learners, or and so I just wondered about that. Could you talk about that?
Oh, that's a good question, Robin. Let me see if I understand the nature of the question a little bit. So is the question about like how, like, do LAs have a perception of the people that are in front of them that they're teaching computation to, and does that color the way that they think about teaching computation?
Yeah. Yep.
Yeah. Oh, great. That's a great question. I do not have an answer to that question because we only interviewed students teaching in one context, which was the engineering physics course. And so the vast majority of those students, like 80% of them, are engineers. The other like 20% are physicists and mathematicians and chemists. And so the population is, from the disciplinary side, is relatively homogenous at that level, in the sense that like they're all kind of aiming for the same thing, right? And so an interesting study would be a comparative study in understanding the perceptions of LAs working in maybe our life sciences course, and whether they have a different way of understanding what they're doing. I don't think it was prevalent in the data that we collected, but also we only collected data in one context.
Cool, thank you.
Yeah.
Since we just have one more question in the queue, why don't I go ahead and ask it before we just open everything up? And I see that Corey's still here. Does the strategy of having people write code to solve physics problems possibly leave out those without a privileged background in computation?
That is a great question. So I will say one of the things that we've tried to do is we have tried to build structure in place in the groups, like for the introductory course, so that there's a support system so that students who have less of a background in computation are working with students that have more of a background in computation, and that the structure of the groups are such that there's a discussion around the decisions that are being made with regard to writing code. So I can show you actually well, maybe I'll show it when we open it up, because I have a video clip that I think speaks directly to what Corey is talking about, from a study that we did where we looked at students writing code, in particular a student who is a computer science senior taking an introductory physics course with a group of students who are all freshmen. And it's a very interesting clip that I think speaks to it and maybe opens up to like better pedagogical strategies for dealing with those kinds of situations, because it is a very important one to deal with.
Super cool.